problem that we're trying to do. And we have a ladder leaning against the wall as shown. And this ladder slides down the wall at a given angular velocity or angular speed of the top, let's say, center point of the ladder at a given speed of 10 inch per second. Now, this kind of problem actually you did first time in your calculus class, which is called the related rates problem. So the thing is that you're given the length of the ladder and you're given the velocity, for example, of the top point and the initial position of the top point, and then you're asked to find the velocity of the bottom point, etc. So it was based on the fact that the length y squared plus z squared is equal to a constant, and that constant is the length of the ladder squared. And from there, you started differentiating and getting the velocities, and the acceleration is needed. So there are different ways of doing this problem, but I want to introduce you slider joint and point curve joint in this problem, and therefore I'm going to do it in the way that may be rather awkward for you, but that's how I'm going to do that. The only thing that I need, as I said, is the length of the ladder. Of course, the initial position is important. It affects the results. In that sense, it's important. All right, so I will try to make this in 7 inches and then 0.5-inch radius on the top and the bottom, or roughly the wall being of that size. Incidentally, the formulas that you did in your calculus class or your probably dynamics class, it's going to tell you that the velocity at the bottom point is given by this expression and acceleration by that, based on the approach that I gave you. And they're plotted here. Okay, so let's go ahead and let's go to CATIA, and I started with a product file, and then immediately I'm going to save that file, save management, save as, desktop, desktop, new folder. I'll call it uh, sliding ladder, and this is June 5 lecture. Okay, let's do it in that folder, put everything in that folder. All right, let's insert the wall first. So actually, I'll do the ladder first. So insert insert a new part in there, and I'm going to call this thing the ladder. Right click properties. The name of the part is down here, or part number. Oops, right there, ladder, and the instance is up there, ladder. Okay, we make it. Double click on the part right there. You're in part design, so on a convenient plane, let's say on that, uh, yeah, on that plane. Why is that plane? I will draw something that looks like my ladder, and it looks like so. We'll dimension it in just a minute. Now notice that I was going to make a circle here, and I missed the opportunity. Left click, hold down, and drag a little bit. But that's okay. You can always go to here to sketch tool and clear it up right there. See that? You come down here, and then left mouse button down, drag it a little bit, and it turns into a circle. Otherwise, you do it with what I just showed you. Okay, let's put some dimensions and dimensions. This line is 7. Wait a minute. What was it? 7. Yeah, 7 inches. 7 inches. And these radii are 0.5. If I change this thing to 0.5, the other one I think automatically is, well, it didn't because I don't have a parallel constraint, so that's okay, 0.5. There, this is the ladder. Exit, and I'm going to pad this thing by, let's say, 1 inch. Okay, so pad it by 1 inch. Uh, Make it 0.5 inch. 0.5. All right. The other thing that I'm going to do, I'm going to create 2 points, one at this end, one at that end. So let's do in this part, in this ladder part. So click on the point, and there are different ways of making the point. So I'm going to use the circle and spheres ellipse center. So I select that. So notice that the point is going to be created right there, and I do another one on the other side. The reason is that I want to find the velocity of this point, for example, while the point on the top is sliding down uh, the wall, kind of. So this is taking care of it. So let's go to the product immediately, product level. See that? Double gear, click on the floppy, and this part is going to be fixed, or not fixed, but saved. So insert a new part, say no, and I'm going to change this thing to wall. Right click properties, wall, and wall down here. All right. So let's double click on the wall. We're going to go into part design. I'm going to be making the wall. So on this vertical plane, I will sketch something that looks like the L that you have, making the wall. So perhaps something like that. There is the wall. There. Exit. And once again, pad it. Let's make it 0.5 inch. 0.5 inches. They don't have to be the same width. In fact, the width has nothing to do with the kinematics of the problem. Now, you might wonder why, but just be patient and you see the rationale behind what I'm going to do. Notice that this point, when the ladder is leaning against the wall, the way I've constructed it, this point is always half an inch away from the wall. And that point is always half an inch from the horizontal wall. Now, I'm not going to worry about that because I will do slide curve joint, which is that curve at the end slides along that line. But for this point, I'm going to do a point curve joint. So I'm going to draw a line, straight line here, which is half an inch from the wall. And eventually I make that point to always slide, not slide, but move along that line. So here's the reason that I'm going to make this line for you. I just explained it. So on that plane, on that vertical plane, I will sketch a line like that. Okay, something like this. I'm going to make sure that it actually goes, it touches at the bottom point. So, so this point, although it's not important, but I will do it anyway. This point, control that point, that line. We're going to make it coincident so that it lifts it down and puts on it. Okay. And let's see now this thing, let's make it about 8 inches. Okay, 8 inches high, maybe 9 inches high. There, I'll make it 9 inches high. All right, fine, 9 inches high. Very good. That's pretty much it. Exit, and that's it. So let's put it in a good isometric view. Excellent. We go all the way on the top, all the way on the top. Click on the floppy. Everything. Oh yeah, I forgot to actually put this thing half an inch away from the wall. So let's go back to that sketch. I forgot. It just that it looks nicer when we do it like this. So the dimension from this line to that line, half an inch, 0.5. Good. Now exit and save. This is in case the CATIA crashes, power is lost, we have stuff. Okay, let's go to product, double click on the top line and then floppy. Okay, good. So now we're going to go, assembly constraint. The first thing we're going to do, we're going to fix the ladder. So use the anchor to fix the ladder. This is assembly constraint. What I've done here is close the stuff that I don't use very often for these problems. So I've constrained, which is extremely important. And I don't even need this. I don't even need that. Okay, so we have the move toolbar and update. Okay, and a split in case I need it. I just erase. I just uh, you know close everything else that I don't need. All right, good. So we're gonna go to we anchored this. Now we're gonna put this point on that curve. So point coincidence between this point and that line and update. Okay, good. Now this, I want to bring this surface and put it on that surface. And the way to do it is by using the contact constraint that we have not used so far in the course, in this part of the course. That's not the same contact as FEA. So that face and this face, notice that there is external and internal. This means that they're externally going to be contacting each other. If one doesn't look good or doesn't look right, change it to the other one. But this is, I'm sure it's going to be okay. Right. The only thing is that I don't want this guy to be at the bottom. I'm going to move this thing up. So let's use the move toolbar and manipulate icon and make sure this check box is this box is checked, because when I move this thing up, translate it up, I want these two to remain in contact with each other. So I'm going to say translating direction Z. This is direction Z. I'm going to drag this and notice that when I move it up, because this box is checked, these two stay in uh, contact with each other. Otherwise, if I did not do that, this ladder would horizontally move up in a horizontal position. Okay, good, good. Let's make sure one more thing. I noticed that it is possible that for some reason, because of what I did, these two are not flush. Okay, you can see that. I want them to be flush, or these two are not flush. So to do that, I can say coincidence between this face and that face and update. It will push this thing in. Let me show you here. Right now it's off that plane. But when I made coincidence between this plane and this plane and I update, it just pushes it and everything is going to be the way they are. And this last one, I really don't need it. Okay, I can delete it because you will see if I left it there, it will lead to what is called a planar join. I'm gonna delete this last one. Okay, good, and that's pretty much it. So let's save everything. So now we're gonna go to uh, digital mockup, DMU kinematics. We're going to go into the new workbench, which deals with kinematics and stuff like that. So let me move these things out of the way. And I don't need this. I'm going to close the stuff that I don't need it. The important things that I need are these toolbars that are kept here on the top, okay? And of course, in case I need the update is also there. And this knowledge toolbar. This knowledge toolbar generally in the utility position, uh, row at the very bottom. Okay, good, good. Let me also move the knowledge up, because if you want to put physics into the problem, you need this knowledge toolbar. All right. Now, first of all, I put some constraints in my assembly design, and I want to turn them automatically into joints. So you click on the magic wand, this auto create, new mechanism, mechanism number one, auto create, and you see that some kinematic or some mechanism was created. The degree of freedom is one. Let's look at our joint, and you'll be surprised. It says revolute joint. If I had not deleted incidentally that other constraint, you would also get the planar joint probably. And though this is totally nonsense, okay? It happened because of what I have here, and I don't need it, so I'm going to just delete it. Just gone. I don't want to delete the constraints in case I ever have to go back to the assembly constraint and I need it for, oh, they say, I should have said do not delete. Yeah, just a second. No, cancel. I want to delete this. Do not delete the children. Do not delete the children in case I ever need it. Okay, good. That joint is gone. Now, what you want to do is to create a point curve joint. So if you look in this toolbar, of all the joints, you have the point curve joint right there. In order to be able to create a point curve joint, the point must be on the curve, and it is. If not, otherwise you get a message saying that there's a gap distance between the point and the curve, and you won't be able to do it. But here it is. It is the point is on the curve. So curve is this line, and the point is that point right there. Okay, say all right. I will come back and do this thing length driven, but not now. We'll do that later. And then, although I could have drawn a line here and that this said this point stays on that line, another point curve joint, I'm going to do it a different way. I'm going to do it using slide curve joint, slide curve joint. So this curve slides along that curve. By the way, notice that this doesn't have a command associated with it. Point curve does, but not slide curve. We say okay. So here we have a point curve and a slide curve. Degree of freedom is 1. And in order to do the rest of the problem, we have to turn this thing into 0. Now remember, slide curve does not have a command, but point curve does. So double click on it, make this length driven, okay? And then we say okay. Mechanism can be simulated, and let's see if it works. So here is the simulation with command manually. Single degree of freedom. Incidentally, notice that this did not start all the way from 0 because the 0 of this line is way on the top. Okay, so it's actually at this location that I brought it to is 4.1248. This comes into the play later on. So let me record it here. 4. Well, I have to write it down because we're going to need this number later on. 4.1248 inches. That's because when I put the point on the curve, I just happen to select that location, and that's what happened. Now, good. Okay, so let's see. You go this way, this goes down, and obviously you go this way, it goes up, further up. Okay. Now, if you want, you can put this thing in the very top, and in fact, this is what I'm going to do. Okay, if it's bothering you, and you want this thing to be, somewhere on that wall, you have two choices. You can make this the length of this wall higher, or because this wall, this vertical portion does nothing. It's just this line is doing all the work. Okay, so if I put it at position 0, then I guess I don't need that 4.1248 anyway. So we say okay, starts there. Let's double click on it. Oh, not this. Yeah. All right. Now, so obviously it is manually it is working. Let's go and create a simulation. Mechanism number 1. This is even not at the point, see, this is not at the point 0, it's 1.5. So this distance is 1.5, and I need this number, 1.5. 1 point, I may need this number 1.53. Okay, good. So we say okay. Let me see if I drag this thing. It doesn't make a difference here. Reset. Okay, good. 1.53. So that distance is 1.53. Okay, that's fine. You just give it the way it is. Now, I take this sliding bar and drag it so that that thing moves and it goes all the way to the end. Okay, and then insert. Remember, we have done these things. Insert, rewind, and change this thing to anything but one. And if you want to move it, continuously in one direction, it goes like this. But if you wanted to loop it in two different directions, excuse me, it goes like so. There are no physics. This is just a cartoon. Okay. So we stop this thing and rewind it and say okay. Now we're going to put some physics into the problem. All right. So if I go and click on f of x, this thing opens up. And then when I click on the mechanism, only the stuff related to the mechanism pop up. There is time and there is a length. And this length is that distance 1.53. Right now it's 1.53. However, what I want to do is I want to move this thing down. So I'm going to say this distance, that distance is equal to, not 1.53, add a formula, equal to 1.53. Don't forget inches, dimensions must add up properly, or entities must add up properly. So 1.53 inches plus the velocity was 10 inch per second, inch divided by 1s. Or if you want, you can write 10 times 1 inch over 1 second. That's entirely up to you. Look, I can write it like that, or I can write it as 10 times 1 inch divided by 1 second. You just have to make sure that whatever you do eventually adds up inch equal to inch, and there are no syntax errors. If I had left out probably probably that star, I don't know, it might have given me an error or something like that. We can try it. And then times time. Time is right here. Double click on it, it puts it right there. And if there are syntax errors, we're going to get it up right here. It says they're not homogeneous. So, oh, I forgot this. Oh, there's cancel. No, 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 no. There's, oops. Let's try it again. Let's double click on this. I had an extra I here. That's what it's saying. I don't understand what you did. So this is times 10 times, not 10 I times. So you just left it there. And no errors. Oops. Is this something? Let me see for a second. This is good. Active. It says no. Let me see for a second. This is, oh, we can, that's all right. Let's go ahead and see what's going on. I don't like that no message there, but that's okay. Oh, this is the law. Okay, let me right click activate. Something must be wrong here. Uh, let's try to make a change here, see whether it makes a difference, because I don't like the fact that it says not active. And let me, I don't think it has anything to, I'm pretty sure it has nothing to do with what we did. 10, okay, that's what I did. 10 inch, 10 inch divided by 1 second. Okay, 1.53 inches plus 10 inch divided by 1 second times time. Yeah, the, see this thing, I thought that updating this would come on. You know what? I don't like this, so let me delete it. Let's do another one. Okay, try one more time. On the mechanism right there, this is the dimension, this is the length dimension. Add a formula equal to 1.53 times 10, 1.53 times inches by n plus 10 times 10 inches divided by 1 second times time. I'm hoping that I won't get that on the time. Double click and say OK. Yeah, look, I don't know, that business of changing the units and then doing it again, it messed it up. It should have worked. It will work, but I did it again and just I don't have this deactivate sign there. Very good. Let's save it, by the way. All right, so we're going to do simulation with laws. So let's do simulation with law, and then later on we're going to put a sensor here and plot the velocity and stuff like that. So let's do simulation with laws. Now, default is 10 seconds. So 10 second times 10 inch per second, that's going to be 100. That's a lot of, so let's make it 1. That's a lot of distance that's going to travel, which it won't, obviously. So that's going to be maximum of 10 inches. So this is, even this is too much, but we'll find out. So if we play this, actually it reaches down below before 1 second. You know that, but I'll just leave it the way it is. That's okay. That's okay. That's fine. So we say close. Now we're going to create a sensor here, speed acceleration sensor right there. Speed acceleration, click on it. This is the ball rolling down the hall. And I want the reference product is that wall. And the point that I want to plot something is going to be this point. And it's going to be the y component later on, y component of the velocity. Okay, so that's good. And now we're going to go and click on the simulation with laws. Simulation with laws, activate sensor. Activate sensor. Now, if you don't get the whole thing, let me cancel that for a second. We did create it here, right? Yep, it's right there. So let's try it one more time. Where is that ball rolling down a hall? Down. Oh, we already have it. I don't want to do another one. So let's see. Let's double check on this. Yep. Activate sensor. Yep. Activate sensor. So what do we want? We want the only thing we want is the y linear speed. Y linear speed. Okay, y linear speed right there. See, notice change from yes to no. I'll move this thing out of the way. Let me move the tree up there. And then we're going to play. Remember, 1 second actually it's too long a time, but that's okay. We're just going to go. All right, and we can make this graphics, and it's going to show you the velocity component of y of that point as a function of time. There we are. Okay. Now you might say, "Oh, why does it look like that?" Okay, so what we can do is, let me close this. Okay, let me change number of steps. Rewind this thing. Make sure you clear the history. And let's change this thing to more steps, 80 steps, okay? Everything is the same. You just like clear the history and change this thing from 40 to 80. Play it. Notice that it actually looks like it did go further, but that's okay. Graphics. So you can cut down on this amount. This is actually the discontinuity. This is actually discontinuity in the the speed. Basically, suddenly jumps to a certain value. So anyway, just remember on the test, if I ask you to generate such something like that on the final exam, first of all, zoom out here. I did zoom out, the usual zoom out, and then you're going to go print screen, start a, for example, a Word document, paint the stuff, paste the stuff in it, file, file, save as. We had a folder there called slider, no, not slider crank, slider crank. I don't see it here, so let me go ahead and it was called sliding ladder, right? So browse sliding ladder. That was from yesterday. Sliding ladder, desktop, sliding ladder. Must be somewhere down here. Sliding ladder. Yep. My plot of y velocity versus time. Remember, on the final exam, we will ask you to generate stuff, graphs like this. I don't want any more than I asked for or any less than I asked for. If I say, show me the y component of the velocity as a function of time, this is the only graph that must be on that paper. Okay? Nothing else.